Hello everyone, welcome back to the latest lecture session. Let's get right into it. We were discussing generic aspects until now. We looked at the video of the IIT Roorkee sewage treatment plant just to get your juices flowing, right? And now we are going to get into the crux of the issue, right? So wastewater treatment, right? What is it that I'm trying to do or degrade? So I have water that's high in total suspended solids, has some dissolved solids, total dissolved solids, the sum of which will be total solids. And typically the issue is that it will have a lot of organic content, right? Organic content, let us say CHO, right, XYZ stoichiometry. And this, when I release into the oceans, what is going to happen to this organic content? Not oceans, pardon me, the surface water bodies or such. It will undergo degradation, and how is it? It's going to use the most common electron acceptor out there, which is oxygen. And then the microbes are going to lead to try to achieve this particular reaction. Why is that? They want to get the relevant energy that will be released from this redox reaction. This is nothing but redox reaction. Carbon relatively reduced form is now being oxidized or mineralized to carbon dioxide. In this process, the compound, not compounds, the bacteria are going to get the energy. So that is going to happen in nature. That is what you see when you throw your waste out or such, right? If it is anaerobic, it is going to start to smell too, right? So that is one aspect to keep in mind. But again, this is an aerobic process, as in being done in the presence of oxygen. So if I let it out, or the waste, untreated waste, into the river or surface water body or such, leave aside effects on humans, it is obviously going to lead to the collapse of the aquatic ecosystem. Other than that, the relevant pathogens will be recycled back into our own drinking water supplies, and we are going to be affected and such, let us say, right. So that is something that we already see. So what do I want to remove in general? I obviously want to remove this organic content. I also want to try to kill the pathogens or make them inactive, let us say. But here I have organic content in the form of some suspended solids, some dissolved solids also, right. They will be dissolved, and some of it can also be suspended, and then you can have inert material also, right. So organic content present both in the form of dissolved organics and suspended organics, and also I want to take care of the pathogens. So how do I do that here? So we have a schematic out here. You might have seen, at least in India, let us say, manholes overflowing and such. Other than poor design, one reason that leads to such choking of manholes and such is that people dump a lot of inert waste. One example is dumping of plastics, let us say, and that chokes up your pipeline or sewerage network, and then you are going to have overflow or such. So it is on our hands. That is something to note. And so all those bigger particles, branches, leaves and such, we want to remove using the bar screens. If not, they are going to affect your other machinery down the line in your wastewater treatment plant. And then grit, and again relatively bigger particles, let us say, and such, you want to remove them or take care of them out here, let us say, right. Easy to remove, and they and such. Then you are going to have particles that will or can settle down by gravity, but can take a lot of time. So you can add a coagulant and flocculant, but in wastewater treatment typically they do not add coagulant flocculant, but some people do. And then you are going to lead to have or settling of your relatively heavier particles here at the bottom, and that goes to sludge thickening. We looked at the video in the last session, where at the end of the video I showed you a particular filter press where the sludge that was collected from that aeration tank of that particular sewage treatment plant, that it settles down, right. It is heavier, it settles down, and that goes to this sludge thickener, because you want to decrease the volume and the what is it now, increase the density, let us say, right, and such. So it goes to the sludge thickener. So here what is it that we are trying to do here? Here we are trying to remove as much suspended solids as you can, right, primarily suspended solids. Along with this process, obviously some of the organic content is also going to be removed. So here we will have, let us say, maybe 30% BOD, but considerable removal of suspended solids. After that you still have a lot of organics. Again I just used the term BOD. It is biochemical oxygen demand. So it is nothing but what do we say, a way of understanding how much organic content is there in the water sample, but we are trying to look at it in terms of oxygen demand, as in how much oxygen will this particular waste or the organics in that waste oxygen demand, how much will that exert, let us say, right, how much oxygen will it be consuming, right. In that terms we are going to look at it, biochemical oxygen demand. Why is that? Again because if I dump this waste into the nature, it is going to consume the oxygen. So BOD will give me an idea about how much oxygen can be consumed, right. Biochemical oxygen demand, indirect indicator of the organic content, let us say, right. We will look at how to conduct this BOD test later, but I just want to mention that. And then we have this activated sludge biological treatment. Activated sludge, what is all this? Sludge, if you remember, I put in a beaker, right, and this was after aeration, and after some time you had relatively clear water at the top and most of the sludge or the bacteria settled down to the bottom, let us say, right. So that this is what we are referring to as sludge. So what is the role, or why do we need this sludge and why do we need to activate it? For example, you see that after this aeration treatment here or aeration zone, it goes to the secondary settling and then the sludge is settled down. That is what you saw in the beaker. The settled sludge is some of it is recycled back into the what is this, aeration basin, let us see, aeration tank. Why is that? Because the waste that is coming in, the waste that is coming in, let us say, does not have, the waste that is coming in here does not have enough microbial content, let us say. So the kinetics of your particular degradation of organics is going to be relatively slow. So you want to increase the concentration of the microbes that are present in your aeration basin, right. So that is why you are going to recycle some of this settled sludge from here back into the aeration tank, and the other obviously goes into that sludge thickening, and after that it goes for sludge digestion or composition before being given to farmers or used as fertilizer, right. So this is the biological process out here where most of the BOD is degraded. If nutrient removal as in nitrogen and phosphorus removal is also required, that you will have another stage here, or you can tinker with this biological process right here to remove nitrogen and such. And then chlorination, typically you now people are moving away from chlorination of at least treated wastewater. Why is that? Because you have harmful disinfection byproducts, but we will not discuss this now. Chlorination or disinfection is carried out. Why is it? You are going to have to take care of the pathogens here, right. So that is why you have chlorination, you can have UV for disinfection, right, and such. So that is something to keep in mind. Let me just give an overview of what we have out here. So preliminary treatment, where plastics, tree leaves, branches and such are removed out here, bar, screens and grit chamber. We will have good pictures and such later. Primary settling, relatively bigger particles, quite a few wastewater treatment plants sometimes do away with this primary treatment, okay. And then you have the biological process, let us say, again here we have to have the sludge, but for the sake of easier understanding I removed it out here. So here biological process where most of the BOD or the organic content is removed out here, and here most of the suspended solids are removed, and here most of the pathogens are removed. So as you see, primary treatment, secondary treatment and then disinfection. Sometimes you will have tertiary treatment if you also want to remove nitrogen and phosphorus, let us say, right. So that is something to keep in mind out here, primary and secondary. In India mostly we have only up to secondary treatment. Even if we had a sewage treatment plant in the first case, we only have it until the secondary treatment, and typically they are poorly run. Why is that? Lack of knowledge, and again people think that microbes are like a machine, so you can treat them poorly during the night and in the morning they are going to wake up and do the job. That is not how they work, right. They are similar to maybe humans or any other living organisms You take care of them, the system thrives, right? A good, what do we say, microbial population is going to thrive, and then you are going to have a well functioning sewage treatment plant. Microbes, again, living organisms, right? You don't, what do we say, look after them, they are not going to be able to do what it is that the plant was designed for. So that's one thing that we always see in our wastewater treatment plants. And another thing is that, especially in those cases where industries are connected to the relevant common effluent treatment plant and such, what do industries do? They are supposed to pre-treat it so that at least some of the more toxic and hazardous chemicals are removed before the waste is sent to the sewage treatment plants, not sewage, common effluent treatment plants and such, which are typically based on the same principles that we see here. But what do they do in the night? They just let all the toxic, very low pH waste or high heavy metal laden waste or inorganic laden waste into the relevant stream. That ends up coming in contact with your bacteria. The bacteria can't do the job or they die, let's say, right? And again, it leads to ruin of the plant, and that happens quite often in India. But hopefully people will realize that we are shooting ourselves in our own foot, let's say, right? Or you people listening to this class will now act as relatively more aware and knowledgeable citizens. So we looked at wastewater, and in water, what is it that I am concerned about? So in water, at least in theory, the issue is that we presume that the organic content is relatively less, okay? But again, this is in theory. In India, that does not turn out to be the case, especially when water treatment is from surface water bodies like rivers or lakes, let's say, okay? So we assume that organic content is less, and then what is it that we are trying to remove? We are trying to remove suspended solids, if there are any, right? And then we are going to try to kill the pathogens. So that's what we are going to achieve. So suspended solids, how do we remove that? As I mentioned, preliminary treatment, bar screens and such, we are not going to discuss this. So we can have just particles settling by gravity, let's see, right? We had the example of bottle of or glass of water and particles or soil, put into that particular glass of water, and after some time, most of it settling down, but still some particles will be out there, let's say, right? Because they take more time, let's say. Again, different types of settling, we will come back to that later. So here we will let gravity do the job for these particles. But what about these particles, let's say? How do I get rid of, or how do I get these particles which are relatively small in size but can still be removed, or can still be what do we say, pulled down by gravity, if I may say so, but will take a lot of time. What will I do? I have these flocks, right, and they are going to have a charge on it, let's say, and I am going to try to neutralize the charge here, right. Typically they have a negative charge, and that is why they repel each other. So I am going to add a coagulant, let's say, typically that will have what do we say, positive charge, let's say, that is going to or can release positive charged ions, let's say Fe2 plus, not Fe2 plus, typically Fe3 plus, let's say, or Al3 plus or such, let's say, right. Charge is going to be neutralized out here, right. The surface charge is going to be neutralized, and then the particles can, this is a plus, I am trying to write, it looks like a 4 here because of the way that I seem to be using the pen. So then the particles can come together, they can coagulate, let's say, right, and then bigger particles, they can be removed by sedimentation. So first you are going to add a coagulant, right, Fe3 plus or Al3 plus. So you are going to have rapid mixing and coagulation, right, when you are neutralizing the surface charge, and then you are going to have flocculation when these particles come together and form flocks. Here you are not going to mix it rapidly, because if you mix it rapidly, these particles are shear, I guess, right. They are not going to form flocks. So here you are going to have gentle mixing, right, gentle mixing, and then once you form the bigger particles, and then you are going to stop stirring, and you are going to have sedimentation, right, and obviously you need to treat the residuals. And then you are also going to have, let us say, relatively other smaller particles which can't be removed even by sedimentation. So you want to have, let us say, different filtration process or techniques. One common way of filtration is by using a sand filter, right. There are different kinds. Sand filter relatively common, let us say, right. Again, obviously if you do not do this and use a sand filter directly, yes you can, but keep in mind that your sand filter is going to be choked very often. So, what happens is, it is not as if, let us say, the size is 20 micrometers or 30 micrometers and everything above 30 will be stopped, everything below 30 will go down. It does not work like that. You will typically also have a biofilm developing on your sand, and it is not just training, let us say, sometimes the biofilm will absorb and degrade some of the organic content here and such, and the size of this particular pore also decreases. You are going to have straining and other aspects. So, relatively smaller particles also can be removed, let us say, right. So, sand filtration, what have I been doing until now? I have been removing the suspended solids until now. And then obviously the final step before I send it to the water distribution network is that I have to remove the pathogens, let us say, right. So, that is why I disinfect it, typically either Cl2 or HOCl, right. Source of oxidizing agents, both are oxidizing agents. Nowadays people are going to UV and rarely also ozonation. Ozonation, why? Because it can oxidize the organic content present, if any, without leading to formation of harmful or carcinogenic disinfection by products. When you use Cl2 or HOCl though, you can lead to formation of disinfection byproducts, right. So, that is something to keep in mind. We will look at this. This is for general water treatment, but obviously as I mentioned, we will also look at ion exchange and what else, I think different kinds of ultrafiltration and so on and so forth, let us say, right. So, this is for surface water treatment. Let us move on and see what it is that I have out here. So, the content we are going to discuss over the next couple of sessions, that is what we have out here. So, obviously we need to look at and understand concentrations and material flows, we will just touch upon that. And obviously material balance, I request everyone and urge everyone rather to pay great attention to material balance. You will use this, at least environmental engineers will use this a lot, when they go to pursue masters or PhD. And at least in this class also we will be using it a lot in the wastewater treatment related aspects, let us see, if not in water treatment, right. Let us see what it is that I have. So, with respect to concentrations, we can express this in different ways. Let us say I have this, right. So, A moles react with B moles of B, A moles of A react with B moles of B to form these moles, right. So, I can express the sometimes concentration is, at least in air, is expressed in terms of mole ratio, right, that is something. Mole, I guess, right, what is it? Avogadro's number of these compounds, 10 power 23, right. That is based on trying to see that the molecular mass and the mass in Daltons is the same. So, mole, sometimes people use that, but typically in water or wastewater we do not use that a lot, pardon me, right. And another aspect is mass. So, either milligrams of the compound per gram or such, or milligram per kg or such, let us say, right. Or let us say sometimes though I have written it as volume here, I will also use it in terms of amount per volume, as in I can have mole per liter, right. So, that the unit is molar units, let us say, moles per liter, let us say, right. And with respect to mass, sometimes we come across different kinds of units like this, milligram per liter, let us say, mass per volume, right. Moles per volume, mass per volume. I typically would like to write it as mass per volume because it helps me in understanding, but again different ways for different persons, let us say, right. Milligram per liter, let us say. And 1 liter of water, let us say if I am dealing with water and assuming the density to be what now 1 kg per liter, let us say, milligram per kg. Here when I write it this way, people will be confused. So, the way I write it is, let us say if I am talking about calcium, let us say. So, I have milligrams of calcium, let us say 100 milligrams of calcium per liter of water, right, per liter of water. So, mass per volume of water. So, if I say it is 1 liter weighs 1 kg, let us say 1 liter of water. So, 100 milligrams of calcium per kg of water, let us say, right. So, here milli is 10 power minus 3 grams, kg is 10 power 3 grams, right, of calcium in H2O, right, or in water. So, thus what does this end out to be? This comes out to be 100 into 10 power minus 6, or let me write it this way in the denominator, 10 power 6, let us say, right, per H2O. So, this unit is 10 power 6 and a million is also 10 power 6, right. So, 1 by 10 power 6 is nothing but 1 part per million, right. 1 by 10 power 6 is nothing but 1 part in a million, 1 part per million, right. So, that is something to keep in mind. So, this unit can also be written as 100 ppm Ca2 plus concentration. So, that is something to keep in mind. Similarly, instead of 1 by 10 power 6, if we have 1 by 10 power 9, so billion, 1 billion is 10 power 9. So, it is equal to 1 part per billion, let us say, right, 1 part per billion, let us say. So, that is something to keep in mind, different ways of expressing it. So, one is with respect to moles, we have molar. In typically when we are talking about chemistry and relevant conversions, we talk about molar basis, but for the layman typically they understand it better in terms of mass per volume in as in milligram per liter. Rarely do we express it in terms of volume. Sometimes, especially when we are talking about hardness or such, we express it in terms of equivalents. So, when we say equivalent, what is it that we are talking about? Let us say I have let us say some apples and you have some oranges. How do I go about getting the oranges I want and giving you the apples or such that you want. So, we need to think of it in terms of equivalent. So, one equivalent can be the cost of or the price of, let us say, a set of apples, let us say. So, we are talking about money here. So, we are talking about equivalents in terms of money. So, I will give you, let us say, 100 rupees equivalent of market value worth of apples, and you will give me 100 rupees worth of or equivalent worth of oranges here. So, similarly here let us say equivalent. So, we need to express it in terms of equivalents or some equivalent. So, typically it can be in terms of how much H plus is given out or can be taken, equivalent in terms of H plus, equivalent in terms of what is it electrons, equivalent in terms of electrons, and most usually used is with respect to charge, let us say. So, equivalents in terms of charge, as in you would have seen with respect to hardness or such, we would have expressed rather than writing it as Ca2 plus, we write it as this is 2 plus, we write it as CaCO3 equivalents, CaCO3, right. So, we will look at these conversions and such later. So, that is one aspect to keep in mind, right. For example, calcium molecular weight, how much is that? 40 I guess, right, 40 grams per mole, right. And with respect to CaCO3, 40 plus 12 plus 3 into 16. So, this is 48 and 60. So, that is going to be equal to 100 grams per mole, let us say. Here if we are looking at it with respect to charge and positive charge, it is Ca2 plus and CO3 2 minus, let us say, right. So, plus 2 charge out here, right. So, based on that you can calculate the equivalent weight, right. So, if I have let us say 2 equivalents per mole, let us say, right, what will the equivalent weight be? It will be 100 grams per mole by 2 equivalents per mole, right. So, that is going to be equal to 100 by 2 gram per mole into mole per equivalent. So, that is going to be equal to 50 gram per equivalent, let us say, right. So, in that way you can convert it. I always suggest that you write it in terms of this equivalents, let us say, right. So, that is something to keep in mind. Similarly, you can write it for calcium and once you have it in terms of what do we say equivalents, you can get it done accordingly, let us say, right. Okay. Okay, so let's cover the next aspect. So concentrations, we sometimes look at conversions. I mean, one aspect is, let's say, milligram per gram, right. So 10 power minus 3 gram per gram then, right, or ml per liter or microliter per liter, right. So you have to use these relevant conversions, let's say, conversion factors, 10 power minus 3, 10 power minus 6, and so on and so forth, let's say, right, or liter and meter cube and different conversions. Then there is the other kind, the type conversion, about which I already talked about. For example, molecular weight, let's say, mass per mole, mass per mole of that relevant compound, let's say. For calcium, we just saw that it is going to be equal to 40 grams of calcium per 1 mole of that relevant compound, let's say, right. So that is something that we already looked at. Similarly, equivalent weight, how will we get that? That is molecular weight, for example, again with calcium, 40 gram per mole, let's say, right, into, let's say, calcium 2 charge. Here the equivalents are with respect to charge, let's say. So 2 equivalents per or divided by, right, it has to be divided by, isn't it? 2 equivalents per mole, let's say. So we have the equivalent weight out here, 20 grams per equivalent, I guess, right. So again, this should have been divided, not multiplied by, right. So accordingly, you can calculate the equivalent weight and get it done. And obviously density, but we do not use that a lot. Again, the units of density are mass per volume, right. Typically we assume that the densities are same with respect to time and space, at least in the aspects that we consider out here, let us say, right. So let us move on. This is with respect to equivalents. Before I move on, let us say, sorry about that, we had CaCO3, the equivalent weight was 50 gram per equivalents, let us say. So now for calcium, you had it in terms of 20 gram per equivalents, let us say. So let us say if you have concentration of calcium to be let us say 100 milligram per liter, right. So you can convert it into equivalents in the first case, right, and then use that to convert it into equivalents in the form of CaCO3. Do I have space here? Let us just try that out. I have CaCO3, the equivalent weight was supposed to be 50 gram per equivalent, and again here we are talking about charge, keep that in mind, equivalent in terms of charge, and for Ca2 plus we said that it was going to be 20 gram per equivalent, let us say, right. And the concentration, let us say I have is 50 milligrams of Ca2 plus per liter of this water. So here I want to convert this into equivalents here. So what do I do? So I guess you see the units out here, I want it in terms of equivalents, so I can divide it by this particular value, because it is of calcium, let us say. So into 1 equivalent per 20 grams of Ca2 plus, right. So now I will have it in terms of milli equivalents per liter, but I want to express it as CaCO3, right. So again I will have to multiply it by this value. So I have 50 grams of CaCO3 per equivalent. So let us see what the units will turn out to be. I first have 100 by 20 into 50, right. Milli, that is 10 power minus 3. So this is what I have. So grams of calcium, and grams of calcium, they cancel out, equivalents cancel out. So what are the units I am ending up with as CaCO3 or CaCO3 per liter, let us say, right. So from that I guess 20 into 5, 550s are 250, because we already took what is this, okay, 250 instead of 10 power minus 3, I will write milligram as CaCO3 per liter. So that is what we have. We just converted 100 milligrams of Ca2 plus per liter and we express this in terms of as CaCO3 or in terms of CaCO3, right. 100 milligram is equivalent in terms of 250 milligrams of CaCO3. Obviously, knowing these equivalent weights and such, you can also get it done in a faster manner, but I wanted to show you the way to get it done without any confusion or such, especially if you write the units in terms of milligrams of calcium, 1 equivalent per 20 grams of calcium, and so on and so forth. So, different changes in units. But let us say if I wanted it in molar units, let us say I have 100 milligrams of liter of calcium and I want the units in molar units, let us say, right, molar units. What do I do? So, molecular weight, I know that it is 40 grams of calcium per mole, let us say, right. So, I want this to be cancelled out. So, I have to divide it by this molecular weight. I want the grams to be cancelled out and moles in the numerator. So, 40 milligrams of Ca2 plus per liter into or divided by this molecular weight, right. So, that will be 100 by 40. So, this grams of Ca2 plus cancel out, moles comes to the numerator, right. So, millimoles per liter, right. 10 by 4 I guess is 2.5 millimole, mole per liter is nothing but capital M molar units, I guess, right. Molar units, it is nothing but mole per liter, right. So, that is something to keep in mind. And one aspect is obviously, as we mentioned earlier, when we are talking about stoichiometry or such, you have to use what do we say, the molar units. That is always going to make it easier. If not, you can't use this mass units, right. Why is that? Again, here the units, the reactions are in terms of molar units out here, right. A moles react with C moles to form D moles, right. So, if it is per volume, we are obviously going to see that in terms of molar units out there, right. So, let us move on. What else do we have? So, convergence, we will just talk about this diagram and we will move on. Let us say I have mass, I have moles and I have equivalents, right. So, how can I interconnect or interconvert, pardon me. So, mass to moles, I need to have the molar mass, either divide or multiply, and here I will have to have the equivalent weight or the equivalent mass, and here I will have to have equivalents per mole, let us say, right. So, in that way I can convert from one unit to the other. So, I just wanted to mention that. So, we will move on to looking at mass balances, as in, let us say here I have it at a bigger scale. For example, I want to understand the concentration of a pollutant within this urban airshed which covers this city, or let us say if a pollutant or compound is coming into this lake and going out from this way, or is not going out, but can be degraded inside this lake, how is the concentration of that compound changing with time? Or if this river is flowing and the sewage is coming in out here, and if this is flowing in this direction, what is the concentration downstream, let us say 10 kilometers, how do I calculate that? Or more pertinently, for your wastewater treatment plant, you saw that you have an aeration tank. What is coming in? Your organics are coming in. Typically, we use the term substrate is coming in. You are also recycling your microbes, right? X is also coming in, right? But that is just recycle though, that is something to keep in mind. Then we are going to have the relevant reaction out here. So, how long do I need to run this system, or more or less how much volume is it that I need to design this tank for? So, how will I get this? Only by applying mass balance. But I see we are out of time, so I do not want to start this important topic right now. Once again, thanking you for your patience. I will end today's session.